today both John and I have done some work on measuring crack tip fields with EIC, and again I'd like to point out, as both previous speakers have, both Phil and David, that this work is just in its preliminary stages. We've measured crack tip fields coincidentally with CT specimens again, so hopefully we can find some correlation there. Under various fatigue crack loads. However, in this presentation, we're just going to focus on one fatigue crack, and I'll explain why later. Right, the motivation behind this work is that we all know or agree that linear elastic fracture mechanics gives us a useful approximation to help with many fatigue and fracture problems. However, real cracks are blunt, they're plastically deformed, and depending on the loading and the material properties, have different failure process zones. But we now have many different good techniques for detailed characterization of this crack tip field. And we believe that this can help us generate a lot of data to validate as well as to develop new analytical models to help us deal with fatigue and fracture. So we decided to try and measure what's really happening both close to the crack tip and far away. Now go on to the experimental work that we did. It's quick information on some of the test procedures we did. This was a 7mm thick CT specimen in a 2024 aluminium. The grain size was fairly large, so the fatigue crack wasn't as straight as we liked it to, as I'll show you later. Yeah, the initial WW was 0.45. Fatigue cracking was carried out at a R ratio of 0.1. And as opposed to load shed or reduce the load as a crack, we just started off with initial delta K1 of 15, which was about 2.5 kilonewtons. And we pre-cracked this specimen up to a 5.3mm crack, and then we just tore it to get some tearing crack data. The crack length was monitored using a digital optical traveling microscope, which was a stereo microscope, which allowed us to also do 3D DIC on the surface. And we also did a few tests using the CPD so that we could sort of correlate our crack lengths. And this was the other reason of using a 5.3mm crack, because after that, once we tore the specimen, we could measure the crack and know exactly where this crack is. And that's why I'm presenting with that data. Right, it's a measuring setup. You can see that's the microscope there, specimen, and the 2D DIC, because we ran out of cameras at that point. So we had two cameras attached to this microscope, a single camera with the same CCD, and a 50mm lens, which in hindsight we can afford to buy a longer lens so that we can actually look at much closer to the crack and not lose some resolution. But this microscope system will allow us to measure up to a resolution of 1 micron. I mean, obviously, this was discussed with Pablo last night over the speckle patterns. The speckle pattern requirement is quite different. So for these two images down here, it's just the speckle pattern requirements for the front and back face, if you like, of the specimen. This is for the macro one, this is for the 2D. And this is viewed on the same scale, but for the microscope measurement. So in terms of speckle size, this is probably, each speckle is in the region between 3 to 5 microns, and that's in the region of 10 to 20 microns. So we did the test, cycled the specimen, and at different crack lengths we just took a series of images. We had to slow it down because the cameras wouldn't not very, well, they were not high-speed cameras, so we had to slow the test down to get a sequence of images.
So just to show you a couple of videos showing the macro.
Well, that's after that slide, so well, just go to the results I've said before. 5.3mm crack. We did we're going to show you data from two different loads, 2.2 and 4.5 kilonewtons. 4.5 one was just before the fracture, so that's when we're doing actually a drain typical test for that specimen. I'll show you the near crack tip using the fine speckles and the far field one using the bigger speckles. And we'd like to just highlight some discrepancies between the displacement fields we obtain and the linear elastic solution.
Right. This is just a video of the macro fields. What it's showing you will be the strains in the y direction
During a tearing test. This is at the 5.3mm crack one was decided tearing. So you can see that it's quite characteristic of the strain fields for CT specimen, the double loads, and strain of up to 4%, but this has gone way past the fatigue crack loads.
On the reverse side, this is the cyclic data that we obtained. As you can imagine, on the macro side, we didn't really see very high strain. The strains were in the region of 0.2%. So in the far field ones, you only get the elastic bit and not the plastic. But from the microscope data, you can see the plasticity around the crack.
So you can see that crack there, it's not straight, that's fatigue crack, that's about 5.3mm from, probably play that again. And they hold, that's about 2 millimeters by 2.5 millimeters. In some tests we've got some data behind the crack tip, but we're not showing that here today.
But the data is available if anybody wants it. So you can see from the micro measurements
that's significant, and well, you can measure the plasticity around the crack, and even for a fatigue crack, there is significant amounts of plasticity. This is just a snapshot of the displacement field at 2.2 kilonewtons for both micro and macro fields. This is for the same specimen that's on one side and that's on the reverse side. And you probably can't see that well here, but if you look at the scaling there, the difference from that to that is only about 4 microns. So we get very detailed measurements of this field very close to the crack tip. Whereas from here, I think that's about 20 microns. But what I would say is due to the optics and the distance of the camera and the field of view, for the fatigue crack loads, the displacements were near the limit of the PIC system for the 2D. So what we did then was to extract it's a preliminary investigation. We extracted displacement fields along in the U direction, and horizontally along those 2 white lines, just to compare that with linear elastic predictions. And that's for the 2.2 kilonewton crack. So, apart from very near the tip, most of it is fairly elastic. You can see that the data agrees quite well with the linear elastic fracture mechanics predictions. Whereas for the 4.5 kilonewton crack, you see further away from the crack tip, but this is just along the horizontal line. The data falls away. But what's interesting about this data for both is that even though it's on 2 different sites, we get very good continuity between the micro and macro displacement fields.
So so you sort of just get this continuation quite even about 15 millimeters, about 20 millimeters behind the crack tip. And this is what David was plotting just now, basically log U in log R. And you see that at 2.2 kilonewtons, which is agreements they get quite good agreement, whereas for the 4.5 one, where there's significant plasticity, you get this deviation from the theory. What we will be doing in the future is to plot it for various at different angles as opposed to just at theta equals 0. And we suspect where the characteristics of the two plastic lobes or so, we'll probably get significant deviation from that. So, I mean, just some final comments. The development of the nonlinear displacement field around crack tip can be accurately measured with DIC, especially if you've got the right optics. The resulting data from tests in this 2024, which demonstrates the amount of information that's available, and we've probably not even scratched the surface in terms of analysing what we've got. And we believe that crack tip displacement fields are fundamental to the characteristics of the loaded crack. And before I finish, just like to acknowledge the following. Thank you.